Although mathematicians have been drawing diagrams to aid in the solving of problems since mankind first realized that one could draw in the sand with a stick, it's in this technology age that graphing has changed the methods by which we solve all kinds of equations and inequalities. Hi, my name is Tom Atwater, and today we're going to investigate using graphing calculators to help us solve both equations and inequalities. Let's start with examining an absolute value inequality. Solving absolute value inequalities. Let U be an algebraic expression in X, and let A be a real number where A is greater than or equal to 0. If the absolute value of U is less than A, then U is in the interval negative A, comma A. That is to say, the absolute value of U being less than A is true if and only if the value of U is on the interval negative A to A. If the absolute value of U is greater than A, then U is going to be in the interval negative infinity to negative A, or in the interval A to positive infinity. In other words, the absolute value of U is greater than A if and only if U is less than negative A or U is greater than positive A. Now, the inequalities here can be exchanged. That is to say, instead of a greater than, we could have greater than or equal to. And the same with less than or equal to. Now, let's examine what I just told you looking at a graph. Here we have the graph y equals the absolute value of U. It's the V-shaped graph, which is centered right here at the origin. And it's the blue line going up and going up. And that's y equals the absolute value of U. Let's take the first example that we looked at, which was the absolute value of U has to be less than A. What that means, of course, is that the y value has to be less than A. Well, here's A, and here's the line y equals A right along here. In fact, let me highlight that. So here's the line y equals A. And what we see is that the value for U is less than A for this range right here. In other words, let's look and see that it's between negative A and positive A, which again was the solution that we looked at when we were solving this inequality. That is to say that we were told that U had to be between negative A, and that's what this graph shows us. Well, now let's examine the second problem that we looked at, which was that U, or the absolute value of U, was greater than A. And what we're looking at then, of course, is when is the y value above A? Here's our A, so it's for all of these values here that the y value is greater than A, which corresponds to the x values going out this way and the x values going that way, which is why when we had the solution, in this case, U is less than negative A, or we had U was greater than positive A. Then that's the graphical interpretation of that particular solution for the absolute value of A. I'm sorry, the absolute value of U is greater than A. Well, let's take a look at an example, which is to solve the absolute value of x minus 3 is less than 2. So, in this case, it's like U has been replaced with x minus 3. So this becomes negative 2 is less than x minus 3, which is less than 2. And we go to solve that, we add 3 to each part. And what we have is 1 is less than x, which is less than 5. And so when we go to show that graphically, we draw our number line and spot 0. Then 1 would be approximately here. 5 would be approximately here. And because it's less than without the equal to part, we have to use open parentheses, and then we shade in that interval. And in terms of interval notation, we would write the open interval 1, 5, and that is our solution set for x. All right, well, now it's actually time for you to try a problem. I would like you to solve the problem, the absolute value of the quantity x plus 2 divided by 3 is greater than or equal to 3. Write the solution in interval notation and draw its number line graph. Pause the video while you work on this problem, and when you're finished, restart the video to check your solution. All right, let's find out how you did on this problem. The problem is the absolute value of x plus 2 divided by 3 greater than or equal to 3. So this time when we rewrite this, we're going to have that x plus 2 over 3 is greater than or equal to 3, or x plus 2 divided by 3 is less than or equal to negative 3. And we solve each of those individually. In this case, we need to multiply both sides by 3, and that will give us, those cancel each other to 1. We get x plus 2 is greater than or equal to 9. Subtracting 2 from both sides, we get x is greater than or equal to 7. On the right-hand side, we need to multiply both sides by 3, and we get x plus 2 less than or equal to negative 9. Subtracting 2 from both sides, we get x is less than or equal to negative 11. And we have the or in between them. So now I want to create some space for myself. So we remember x is greater than or equal to 7, less than or equal to negative 11. So we draw a number line. And what we have is 0 for the origin, 7 on the right-hand side, negative 11 on the left-hand side. And what we know is that x has to be greater than or equal to 7. And that would be that section of the number line. And we have that x is less than or equal to negative 11, which would be this section of the number line. Now, in interval notation, what we would have is negative infinity, comma, negative 11, open interval on the infinity, closed interval on the 11, and we union closed 7, open positive infinity. And that would be the interval notation for that example. All right, great job. Now, let's examine quadratic inequalities. We start by solving the corresponding equation, and then we determine the correct intervals by examining the graph. So let's take a look at this equation. Solve 2x squared plus 7x is greater than 15. So we want to solve first that this can be written as 2x squared plus 7x minus 15 is greater than 0. In other words, we've got a parabola on the left-hand side, right? And what we're interested in knowing is when is that parabola positive, which means when does it lie above the x-axis? Well, the first thing to do then would be determine when does the parabola cross the x-axis. That is to say, what are the x-intercepts? And we find that by solving the corresponding equation. In other words, we take 2x squared plus 7x minus 15 equaling 0. And we solve this particular equation, and we do that by factoring. We get 2x minus 3 times x plus 5, and that equals 0. And that means that 2x minus 3 equals 0, or x plus 5 equals 0. And on the left-hand side, that means x equals positive 3/2, or on the right-hand side, x equals negative 5. So those are our two x-intercepts. Now what we need to do is examine the graph. And we want to know, again, when is this graph above the x-axis? When is it greater than 0? That is to say, when it is positive. So let's take a look at the graph. Here we have the graph. And what we know is that this is our x-intercept of negative 5. This is our x-intercept of 3/2. And we're interested in the section that it's above the x-axis. That is, the y values are positive. So what we'll see is that it's the interval that starts negative infinity, comes up to, but does not include negative 5, because we're interested in when is it a positive number, or we would have from 3/2, and it's not including 3/2, up to positive infinity. So to write this in true interval notation, we would write negative infinity to negative 5 union 3/2 to positive infinity. And that would be our solution written in interval notation. All right. Now, in the previous example that we just did, the corresponding quadratic equation factored. But if that doesn't happen, we'll need to approximate the zeros of the quadratic equation, if in fact there are any. In this case, we need to use the accuracy agreement that we talked about earlier, and we write the endpoints of the intervals accurate to 2 decimal places. And let's do an example of where we use the graphing calculator to help us do that. So we're going to solve the inequality graphically, and the inequality is 9x squared plus 12x minus 1 is greater than or equal to 0. So what we would do is actually plug into the grapher using the y key. We would plug in y equals 9x squared plus 12x minus 1. And what we're interested in finding when we look at the graph is does it actually equal the x-axis or above the x-axis. So let's take a look at the first time that happens. Here's our equation, and what we see is that it intersects right here between -1 and -2, and our exact answer, as far as the calculator has to display, is the -1.412023, which means we're going to use the value -1.41. Well, there's another intersection over here, so let's take a look at what the grapher tells us about that. It tells us that the solution for that is right here, and it's positive 0.078689, etc. And for that particular solution, then, we would use 0.08. We would round it up. So our solution, then, written in our interval notation, would be from negative infinity to -1 41/100 inclusive union 8/100 up to infinity, because we were interested in when was it greater than or equal to 0. In other words, when does it actually intersect the x-axis, and when is it above the x-axis? And that would be then our solution. Now I want to look at a very interesting example of solving a quadratic inequality using the graphing calculator. And here it is. Solve the inequality x squared minus 8x plus 16 is less than 0, and solve it graphically. So in this particular case, let's take a look right at the graph, because what we find is this: no points on the graph lie below the x-axis. Therefore, that inequality has no solution. You can see clearly that, yes, it does intersect right here at 4, but it doesn't go below. And therefore, this has no solution. Because, again, there's no values that can make that negative. It lies entirely at the axis or above. Well, we can actually take this idea and extend it to solving graphs which are of the higher order. That is to say, greater than quadratic. So let's take a look at that. Let's solve the inequality 3x cubed minus 12x plus 2 is greater than or equal to 0 graphically. So again, what we would enter into our graphing calculator is in the y key, we would enter y equals, and then take 3x cubed minus 12x plus 2, and then press the graph key, and lo and behold, this is the graph that we would get. We're interested in when is it above the x-axis, that is when it's at the x-axis or above, that is when is it greater than or equal to 0. Well, the first thing we do is we find the zeros, and the first one we're finding is right here, and we can see its solution down here, which we would then round to negative 2.08. And that would be the first solution where it intersects the axis. So now let's find this one right here. And on the grapher, it tells us that it's occurring at 0.16784888, which means in terms of our use, rounding it off to 2 decimal places, we would have 17/100ths for this particular intersection. Let's find the third and final intersection right here. And again, using the graphing calculator 0 function, we see that it's equal to 1.910786. Our answer then is going to be 1.91. So we have found these, or I should say the grapher has found those. We are interested in when does it lie above, or actually at or above the x-axis, and it would be this interval right here, because we're of course above the axis, and this interval going out this way where we are at or above the axis. So therefore our solution in interval notation would be this: inclusive of the negative 2.08. That brings us up to this point, which is also inclusive of 17/100ths, union inclusive of the 1.91, and that goes off to infinity. And so that would be the solution written in interval notation. All right, well, that's exciting that we realize that we can extend the use of graphing calculator beyond quadratics. Great job today. So what we learned is how to use the graphing calculator to help us solve linear inequalities as well as quadratic inequalities. Be sure to work the exercises that your teacher assigns, and we'll see you next time.